Kia ora and welcome to this video on question 2 of the 2014 Scholl Calc exam. Again, two parts to this question with an optional part B. Part A is a quartic equation which asks you to describe the nature of the roots and how they depend on the coefficients. It's quite a tricky problem actually. Part B, a fairly reasonable integral question, just a bit messy to work in exact form. And then the option, a system of linear equations, is it looks fairly trivial, but it requires quite a good understanding of the algebra and how the coefficients of systems of equations affect the types of solutions that you get. So yeah, quite a tricky part. Probably the integral is an easier option to take. Okay, part A. The first thing you need to know in this problem is that whilst it's a quartic, it doesn't have a cubic or a linear term. Okay, the powers are just even, which means it's a disguised quadratic equation. You're told that k and q are real, but you don't know if they're positive or negative. So, solving this using completing the square, x squared minus k all squared gives us x to the 4 minus 2kx squared plus k squared, which I need to take away. Rearrange the equation. And we've got x squared equals k plus or minus the square root of k squared minus q squared. Okay, now our solutions that we're investigating here are the x values. And the question is, how do those x values depend on k and q? Describe how the nature of the roots depend on k and q. So, we've solved the problem apart from taking that last square root. So, you know, I could do that. I could go x equals plus or minus the square root of the stuff. They are the solutions to the problem. The question is, how many do we have, and are they real? Are they purely imaginary? Or are they complex numbers with a real part and an imaginary part? So there's quite a few different cases here, and it might help to just consider the trivial ones first. So for example, if k squared minus q squared equals 0, it's kind of like the first discriminant, right? It's the thing under the first square root. So if k squared minus q squared equals 0, which is the same as saying k squared equals q squared, or k is plus or minus q. Well, what happens there? That square root 0, the one that I've highlighted, so we get x is equal to plus or minus square root k. So if k is real, which we know it is, if k is 0, so it's got like a sub case to it. If k equals 0 for this particular case, then q would be 0 as well, and x is equal to 0 is repeated. It's actually repeated 4 times. It's the only solution. If you look back at the original problem, it's kind of a very trivial one. If q is 0 and k is 0, then those terms both disappear, the ones in green, so you've just got x to the 4 equals 0. There's only one solution to that, and that's x is 0. So it's repeated 4 times. Okay, ignoring that case, if k is greater than 0, then we get x is equal to plus or minus square root k, which is 2 repeated real roots. Because remember, this is a quartic equation. It should have 4 solutions at maximum. And if we've got just plus or minus root k, where k is positive, 2 repeated real solutions. If k is less than 0, and it doesn't, in this case, whatever k is, q is the negative of it. So if k is less than 0, then x is still plus or minus root k, but it's 2 repeated purely imaginary. Okay, so they are very trivial cases of it because it's when k is plus or minus q. Now we need to consider other cases. We're considering that yellow discriminant there, k squared minus q squared, we now need to consider what happens if it's negative. If k squared minus q squared is less than 0, that discriminant is going to be negative. We're going to have the square root of a negative number. So we have complex solutions, we'll have imaginary parts in there, and we're going to get 4 solutions. 4 complex solutions, and complex is used a bit loosely here. Complex numbers include real numbers, because a real number is just a complex number with an imaginary part of 0. Complex numbers include purely imaginary numbers. But sometimes the word is loosely used to mean a plus bi. 4 complex solutions with a real and imaginary part is what I mean. In other words, not real and not purely imaginary. Okay. And that only leaves one more case. This is probably the trickiest one to consider. If k squared minus q squared is greater than 0, so that again, that's the bit underneath the first square root. Well, what you need to recognise is that when you take k squared and you minus q squared away from it, you're getting something that is smaller than k squared. So k squared minus q squared is less than k squared. And if I go up to the structure of my solution here, that square root there, if k squared minus q squared in yellow is less than k squared, then when I square root it, I get something that's less than k. And so I've got k plus or minus something less than k when I consider this whole thing as a whole. And what does that mean? If I have k plus or minus root k squared minus q squared, and I know that this thing here is less than k squared. So if it's less than k squared, when I square root it, I've got something that's less in magnitude than k. So k minus that will be greater than 0, and k plus that will be greater than 0, depending on what k is. So if k is positive, if k is a positive number, then no matter what q is, so long as k squared minus q squared is greater than 0, then k plus or minus root k squared minus q squared is always going to be greater than 0, because we're adding and subtracting from k something that is less than k. Can't be negative. In that case, there's 4 real solutions. But on the flip side, if k is less than 0, then we start off at this position here with a negative number, and we're adding and subtracting something that's less than k. So we can never get that to become positive. So that would be 4 complex solutions. And again, complex is used loosely. It means not real or purely imaginary. If you look at the mark schedule for this problem, it summarizes all of the results in a diagram form and considers different regions for k and q that generate different types of solutions, kind of like linear programming. But yeah, that's a full discussion there. That covers some repeated roots, it covers some real roots, it covers some complex solutions, some purely imaginary solutions. But quite a tricky problem because there's a double square root there that we had to think about at the same time. Okay, part B, the first option. Find exact expressions for the areas labelled below. The first thing to notice is because of the symmetry, A and C are the same, so we don't have to work them out both. We do need to work out some points of intersection. So that's where the curves 9 cosec squared equal to 16 sine squared x. Cosec is just 1 over sine, so we've got 9 over sine squared, 16 sine squared. That's the same as 9 over 16 is equal to sine to the 4. We need to take the fourth root, or we take the square root, then we square root again. So that's sine squared is equal to 3 over 4, or sine of x is equal to plus or minus root 3 over 2. Now, if you get your calculator to work out this, honestly, I would just graph those in the graphics calculator, graph them and find out where they meet, and then see if you can work out the exact form. But this does correspond to a a special triangle. We've got root 3 is the opposite side and 2 is the hypotenuse. Sine is opposite over hypotenuse. Then that's 1, and that angle there is pi over 3. So that corresponds to that dude, pi over 3. And then the other value that you want is 2 pi over 3. So pi over 3 is basically 1, pi is basically 3, and 2 pi over 3 is just a bit bigger than 2. So that seems to match up with the graph quite nicely. Okay, the second thing we need to work out once we've found the points of intersection is what graph is on top. You can see that the graph here, this graph, is heading off to infinity as x gets smaller and smaller, and that's the cosec squared graph, because it's 9 over sine squared, and when sine tends to 0, 9 over sine will tend to infinity. Okay, so area A is equal to the integral between 9 cosec squared, the top function, minus the bottom function, 16 sine squared. And we're integrating that between 0.5, assuming that the scale is telling us the region is between 0.5. Oh, no, my bad. No, it's not. It's between pi over 6. Helps to read the question. X equals pi over 6, which is about 0.5. And pi over 3. Okay, so it looks like a tricky integral, but the first part's actually an achieved question because cosec squared's antiderivative is on the formula sheet. Negative cosec squared antidiffs to cotan, so this first part antidiffs to minus 9 cotan. The second one, hopefully you've followed a few of my videos and you've seen how trig integrals work. The sine squared one, we need to turn it into something that we can integrate. Like, don't write sine cubed over 3, that's a real common mistake. We need to go use this double angle formula. 2 sine squared x is equal to 1 minus cos 2x. So negative 16 sine squared times by negative 8 is negative 8 plus 8 cos 2x, and that's what I'm anti-diffing there. So anti-diffing that, I get negative 8x, and I get 4 sine 2x. Okay, because the derivative of 4 sine 2x is 8 cos 2x. going between pi over 3 and pi over 6. And now I'm wanting the exact form of those areas, I need to sub in these limits. Minus 9 cotan pi over 3, minus 8 pi over 3, plus 4 sine 2 pi over 3. Take away bottom limit, negative 9 cotan pi over 6, minus 8 cotan pi over 6, plus 4 sine pi over 3. Real tedious. If you've got an upgraded graphics calculator, one of the modern ones, then it will do all the exact form for you. If you don't, then you need to start using some special triangles. So for example, the angles for the first bracket are pi over 3. So pi over 3 is 60 degrees. It's root 3, 1 and 2. Cotan is the reciprocal of tan. So it's 1 over root 3. And then sine of 2 pi over 3. We could use a double angle formula for that. Or we could look at a trig graph of what sine looks like and work it out. Sine of 2 pi over 3 is root 3 over 2. So we've got 4 times root 3 over 2. And then we've got cotan of pi over 6. Well, 9 cotan pi over 6 for the second bracket. Well, pi over 6 is just the top angle of the special triangle. It's 30 degrees. So cotan is adjacent over opposite. So we've got 9 times root 3 plus... Oh, there's a little mistake there. Shouldn't have a cotan there. Hopefully you noticed that. Plus 8 pi over 6, 4 pi over 3. And then minus 4 sine pi over 3. Sine pi over 3 is root 3 over 2, so it's minus 4 times root 3 over 2. Okay, and then if you evaluate that, it's really tedious, but if you simplify all those things, you should get 6 root 3 minus 4 pi over 3. Okay, well at least that's what the mark schedule says. Now, the second region, region B, it's the only thing that changes is the limits and the fact that the top function becomes 16 sine squared x and the bottom function is now 9 cosec squared. So our integral's the other way round. We're integrating between pi over 3 and 2 pi over 3. 16 sine squared minus 9 cosec squared. So our antiderivative will be the negative of what we had earlier, which was up here. We want the negative of that because we're integrating the other way around. Okay, and if we do the same thing, we sub in 2 pi over 3 and we sub in pi over 3 and we evaluate it, the exact form is 8 pi over 3 minus 2 root 3. And that will be just for the fourth mark. If you look at the schedule, they do tell us how the marks were allocated. The limits of integration was a mark. The antiderivative of each of the two parts was a mark. And then the areas there, which was real tedious, substituting and finding exact expressions of trig ratios, was just the last mark. Okay, part B's second option, a system of equations. This also came from one of the internal assessments. This exam kind of has the flavour that everything was examinable, every standard, which wasn't necessarily a great thing, especially if you hadn't done the standards. So this assumes your knowledge of the internal assessment systems of linear equations. Okay. So we have c plus 2 times x plus c minus 2. I'm going to just space this out a bit actually, because the first equation doesn't have any y's at all. So leave a gap. C minus 2 times z equals 0. Second equation doesn't have any z's. And a third equation doesn't have any x's. If you know how to solve these problems using matrices and row reduction, that could be a technique to use. In fact, the marked schedule does look at matrices, but I'm going to assume that you haven't seen those because that's more covered at university and also in Cambridge mathematics. So let's assume no matrices. When we solve a system of equations, one of the methods we've got is elimination. So we can eliminate a variable. There's 3 equations here, so if we can eliminate the same variable in 2 different ways, then we make some progress. We reduce it down to a system of only 2 equations, and then we eliminate another variable. One of the ways that we can eliminate is by multiplying an equation through by a number to make the coefficients the same. Another way to do it is to just rearrange one equation and sub it into the other, and that's what I'm going to do. So my goal here is I'm going to try and eliminate a variable by substitution. So if I take, let's just number these equations, 1, 2, and 3. If I take equation 1 and rearrange it, I've got c plus 2 times x equals negative c minus 2 times z. My 2 looks like z there, so make sure you put a line with the z. And that's, if I just distribute the negative, that's going to be 2 minus c times z. And then I could divide. So I got x equals 2 minus c all over c plus 2 times z. Some brackets that aren't actually needed there. Let's get rid of them. Overkill with brackets. Okay, so that's my x in terms of z. Now, I can't do that with any of the other equations because the second equation doesn't have any z's in it, and the third equation doesn't have any x's in it. So, what have I achieved there? Oh no, I can, because if I substitute this into number 2, sub into 2, then I'm going to get c plus 3 all times by x and plus c minus 3 times y equals 0. And I can get z in terms of y there. Move the c minus 3 all times y into the other side will become 3 minus cy times by c plus 2, divide by c plus 3 and divide by 2 minus c, and that's my z in terms of y. And using equation 3, I can also get z in terms of y, a little bit easier. Z equals minus c plus 5 times y all over c minus 5. And just getting rid of that minus there, I could write c plus 5 over 5 minus c all times y. So what I've achieved there is one expression for z in terms of y and another expression for z in terms of y. To use a bit of lingo from the this achievement standard, if we want solutions, then those equations need to be consistently true. Okay, to have solutions, we'll call this equation 4 and equation 5. 4 and 5 need to be consistent. Now, it hopefully is clear there that if y is equal to 0, then z would be equal to 0 in both situations. So e.g., if y is equal to 0, that would give z equals 0 in both equation 4 and 5. And that would also give x equals 0 if we go back to an earlier equation we had. And if we look at the original problem, if x, y, and z are all 0, every equation is satisfied, so it is a solution. There is always a solution, 0, 0, 0, a trivial one. To use some more lingo from the achievement standard, the system is never inconsistent, because there's always a possibility of a solution. But what happens if C is, there are different values of C that are going to generate different things here. So if I make those green things equal to one another, because they should be equal, they're both equal to Z, that would make the y equals 0 thing a bit more clear. Because this is true if y is equal to 0. If y doesn't equal 0, then we can eliminate it, and we get a cubic equation for C. Cross multiplication. Unfortunately, none of the factors on the left and right cancel, they're all different, so I do need to expand this beast out. It's going to be C cubed expand two brackets and then expand a third. Hopefully I've done that all right. So we've got 2c cubed, dealing with that term and that term. We've got minus 6c squared on the left-hand side, minus another 2 is negative 8. So the c squareds actually cancel. In terms of the c's, 5 minus 6 is negative 1. Minus 17 plus 15 is minus 2c. And then the constants, 30's cancel, so we get that. Factor out the 2c. If c is equal to 0, c is equal to 1, or c is equal to negative 1, then this thing is satisfied. And what does that actually mean? Well, we can go back and check, because c equals 0 is quite an easy one to check. If we go back and make c is equal to 0, then the first equation becomes 2x minus 2z equals 0, which is the same as x equals z. The second equation becomes 3x minus 3y equals 0, which becomes x equals y. And the third equation becomes 5y minus 5z equals 0, which is y is equal to z. But that third equation actually was not needed, y is equal to z, because that comes from the first two. If x is z and x is y, then y is z. So this is a superfluous equation, which means we've only got two pieces of unique information of independent info, and there are three variables. Not enough pieces of information to tell us what the solutions are, so there's an infinite number of solutions. And remember I said the system could never be inconsistent. It always had a solution. 0, 0, 0 is always a solution to this. But if c is equal to 0, and it is also the case for 1 and negative 1, then we get an infinite number of solutions to the problem. Here's my GeoGebra diagram which I made earlier. In this case it's showing c is equal to 1, and you can see that the three planes, when you make c1, they all simplify down and they're intersecting along a line. And that line actually goes to the origin because we knew that 0, 0, 0 was a solution, always. Doesn't matter what c is. If c is equal to 0, then we get the same thing happening. We get the solution we got before, again, an infinite number. And if c is equal to minus 1, this solution changes, but again, the planes are all meeting along a line. But if I choose any other value c than that, so slide this off one of those critical values, the planes are now not meeting along a line. See that there's two dashed lines in there now, a black and a blue one? The blue one is two planes intersecting, the black one is another pair of planes intersecting, and they don't line up, they're inconsistent. But they do intersect at the origin, at the point 0, 0, 0. So the trivial solution, once again, is a solution. Okay, so hopefully that helped you understand that. Now if we just summarize that, what would we answer? For these values of c, there is an infinite number of solutions. As the equations 4 and 5 are consistent. We made them equal to one another, so that means that they both tell us the same thing, which means we don't have that third piece of information we need. For other values of c, so any other value of c, and then these coefficients here would not be the same. So we'd have something like 6y equals 4y or something like that, which would mean that the only possible solution for that would be y is equal to 0. Y has to be equal to 0. And in that case, x equals y equals 0. X equals y equals z are all 0. One unique solution. Catch you in the next video.